Yeah, first thing I'll say is if you don't like your seat right now, find a different one. If you have other in-person classes, you'll probably see this a lot. They want us to sort of assign seating. I'm not just going to choose your seat for you, but find one that you like, and I won't enforce it today or anything. But starting probably Wednesday or Friday's class, I'll take a note of where everyone is, and that'll be your seat for the semester. Why are we doing that? Obviously just for contact tracing reasons, right? Figure out who sits next to you. What else? I don't want you to ever feel obliged to come to class. That's why this camera's here. If you miss class, if you can't come, if you're feeling ill or whatever else, I will take that video and post it up online sometime shortly after class. So there's that. Meaning you can turn in homework online. You can do pretty much everything without ever having to come to class. This camera's a little bit limiting. I'm hoping this is a good angle. I don't really know. It limits me to just using this board, so we'll work with it. But yeah. Why are you guys here? Why is everyone taking Geometry 1? Because you have to?
As an elective.
Elective? Okay. I think math ed people, you have to take a year of geometry, is that right? So Geometry 1 and 2? Okay. So yeah, this class is sort of a higher level geometry class. We'll start off the first chapter, which will take us a little while to go through, should be review for you. It should be stuff you've seen before that you've done in a lower level geometry class in high school or something. But we'll pick it up from there. Then you'll start to see new results, stuff you haven't seen before. Everything will be pretty proof heavy, so we'll be assuming you've taken 201 before intro to proofs, you know how to write proofs, or at least the basics of them. I wouldn't expect you to be a proof writing expert at this point. But yeah, we'll do a lot of proofs, so it'll be a theoretical class. And what else do I want to say? I posted the syllabus. Have you guys looked at it? If not, it's pretty straightforward. There's not a whole lot on here that's too exciting. We'll be doing weekly homework, so I'll probably assign them, I think, Friday at the end of the week and make them due the following Friday at the end of the next week. I don't think I want you to turn those in person. I think I'd like you to scan them and upload them, and I can work with PDFs. So we'll do weekly homework. The homework is 40% of the grade. We've got two in-class exams together, making up 35% of the grade. Tentatively, I put the schedule on here, October 2nd and November 13th, but I don't really consider those dates too binding. As we get closer, we'll see if they work well for us. And the final exam, it's 25%. Let's see, makeups. Yeah, the rest of this is really all just a standard required stuff on the syllabus. Any questions? This is the textbook, by the way. Isaac's Geometry for College Students. I'll be assigning homework out of this, so you really kind of need it. I've been told there's an older version of this that used to be printed by a different publisher, and the only difference is it has a different cover. So otherwise, exact same textbook. Any questions? Ask me questions, please. Yes?
Is there an online version of the textbook? Or?
I don't know. I'm sure if you search for a PDF version, you can find it. Whether it's legal or not, I don't know. Any other questions? I have no idea how popular this textbook is. And I say that in the sense of if a textbook's really popular, in fact, it doesn't have to be that popular at all, you can find all the solutions to every single homework question online somewhere. So yeah, speaking of that, the homework, the only thing I expect of you for homework is that the work you turn in is original to you, right? I don't mind if you work with other people. I don't mind if you even look up solutions online. But the work that you turn in should be your own. And I would encourage you not to sort of look up solutions just straight away, right? Think about it first. If you're struggling, then that's fine. If you need hints or a push in the right direction. But don't just look up something and copy it and turn it in as your own. That is plagiarism. So don't do that. But yeah, if you work with other people, if you look up sort of hints or whatever, that's totally fine. But if you do just copy stuff off the internet, There's probably someone in the class that's done the same thing, and you will have the exact same solutions. So, any other questions? Yes?
Is homework gonna be based on the right answer, or is it gonna be more based on completion?
That's a good question.
Because some math classes, they're like, you know, we don't really care if you got it as long as you did the homework.
Yeah, no, I mean, the idea is, there's lots of proofs, right? And the idea with proof writing is that it should be a good, correct proof. You should be learning how to write proofs. And the most important thing, we have a fantastic grader for this class. I'll do some grading too myself. But the grader we have, I've worked with them before, particularly for geometry. And the most important thing when it comes to grading proofs is feedback, right? You can't just X something out and say -2 points. You have to indicate why something's wrong or how you could have phrased something better. So, yeah, correctness is important. Any other questions? All right, I usually don't teach much on the first day. Syllabus, I don't think syllabus week is a thing, but syllabus day is kind of sacred to me. But since we've lost a whole week, I'll compromise and we'll just do a little bit of history. So what are we learning in this class? This is Geometry 1, so it's Euclidean geometry. Who is Euclid? Euclid of Alexandria, I think. He lived in 2,300 years ago, so this makes us about 300 BC. And he really is, he's the founder of geometry. Or father, if you want. Founder of geometry. And what he did is the following. He published a book, really a collection, I think 13 different books, called The Elements. All right, so this is 13 volumes. And what he did in this is he developed what's now called Euclidean geometry. So the Elements is, we attribute it to Euclid. Really what he did is he collected a bunch of works from other people that came before him. He didn't discover much on his own. I believe he provided all the proofs himself, but it really wasn't stuff that wasn't known already, most of it. So anyway, massive undertaking, 13 volumes. Together, all of these results make up what we now call Euclidean geometry. And the Elements, how many of you have heard of the Elements before? Yeah, not many people today, but the Elements is, I believe, ranked as the second most influential text ever. What's the first? The Bible, right? There's lots of ways you can rank influence. I believe in this case, I'm going with the number of editions published. The Element stands at over 1,000. But in mathematics, this is absolutely the most influential text ever. So, one of the most influential texts. And basically, most people don't read the Elements these days, but for about 2,000 years, until the 17th century, I think mid-1850s or so, from the day this is published until about 1850, pretty much anyone who was considered an educated person had read the Elements. Right? This is what people studied. So, I don't want to write that. I don't have a whole lot of space. But yeah, and the reason for that is it teaches logic, right? It teaches you how to think. Whether you care about geometry or not, it still teaches logic and how to think. do I mean by that? Well, he didn't just develop Euclidean geometry. The way he did this is axiomatically. He developed Euclidean geometry axiomatically. What does that mean? What's an axiom? Right? This gets into the foundations of how math works at all, right? He didn't just influence geometry, he influenced logic in general. And what he did is he came up with 5 axioms, or 5 postulates as he called them, of just things that you accept to be true, right? Statements that don't require any sort of proof. We accept that they're universally true. So he had 5 axioms, or postulates. And 4 of them are really quite tame. 4 simple. And I won't go through them, I won't state them. This is really sort of something we'll talk about in geometry too. But the first one, I believe, says something like, if you have 2 points, then there's a line segment that connects them. A statement that doesn't require any sort of proof, we'd all just accept that as, yeah, sure, that's a true statement. Other ones, I think, are something like all right angles are equal. If you have 2 points, there's a circle that's centered at one that intersects the other point. And then there's the famous 5th postulate, which I'll say something about in a second. But this is what he did. He started off with these 5 axioms, and then you ask, based on these 5 things that I'm accepting to be true, what can we say from here, right? What else can we prove? What else logically follows from these 5 statements? And from those 5 statements, you build up all of these other results, all of these theorems, all of geometry. And this is how math is done. This is the foundations of modern day mathematics. You start off with this axiomatic system, and you ask, based on these things that we accept to be true, what else can we prove? Now the 5th postulate has more written about it than probably anything in all of mathematics. It's the 5th postulate. These are nice 4 simple statements. The 5th one is a very long statement. It's weird to read. It's the 5th postulate is, I'll just say it's lengthy and awkward. And I won't tell you exactly what it says. It says something about if you have 2 lines and another one through them and you measure some angles, then those 2 lines must intersect somewhere down the road. It's logically equivalent. It's logically equivalent to what's usually called the parallel postulate today. It's logically equivalent to a much nicer statement that says if I have a line and a point not on that line, then there's another line, a unique line, that passes through this point that's parallel to the original. I believe that's usually attributed to a guy named Fairbanks, if I recall.
Not
Right.
Playfairs.
What's that?
It's not Playfairs.
Ah, Playfairs, thank you, yeah. I don't know why I had Fairbanks in my mind. I was thinking about it last night. Yeah, so yeah, this is Playfair's version. It's usually called the parallel postulate, but if you have a line, a point not on the line, then there's a unique line passing through that point that's parallel to this line. So it's logically equivalent to that statement. That's the 5th axiom. And that's part of the reason so much is written about this postulate. One is it's just written strangely, and the question is, can we write it in a nicer way? Secondly, because it's so lengthy and awkward, and the first 4 are so straightforward and simple, a lot of people thought maybe we don't need this postulate, right? Maybe we don't need to axiomatize this. Maybe it follows as a theorem of the other 4 axioms, right? You can just use the first 4 to prove the 5th, and you don't need to axiomatize it. Turns out, you can't do that. It's not a theorem. So, all of this amounts to lots is written about this. again, I think more than just about anything else in all of mathematics, over many centuries. Whole lot of work went into that. And since it's so strange, and you might not even be willing to accept this as an axiom, then other people came along. People like Gauss and Bolliers, the father and the son, who else? Lobachevsky. These people came along and said, what if we change this postulate? Right? So, what if I don't accept that? If it's changed, how might you change this? Well, what's the statement? If I have a line and a point not on the line, then there's a unique line segment, or a unique line passing through this point that's parallel to the original, right? So the other versions, the other possible versions are, there's no line segment passing through this point. I don't know why I keep saying segment. No line passing through this point that's parallel to this one. Or there's more than one line passing through this point that's parallel to the original. So if you change this, you get what's called hyperbolic geometry. Hyperbolic or elliptic geometry. People resisted that for a very, very long time. Changing that statement and allowing these alternate universes, these other logically what's the word I'm looking for? These other consistent axiomatic systems that give other geometries. This was resisted for a very, very long time. Lots of interesting history there. This is all geometry too. In fact, most of this history and everything I'm talking about really gets into geometry too. Any questions so far? And some of this stuff is really cool. I've got these letters between I forget their first names, but the father and son, these Bolliers, and the father is really urging the son not to go down this road of looking at what's eventually called hyperbolic geometry. And the language they used back in the days is very, very strange. But anyway. So let's go back to here. Let's go back to the elements. So again, people read the elements. Anyone who was considered an educated person read the elements, and it was considered just a shining example of mathematical logic and rigor. Logic and rigor. This was how math should be done, and it still really is how math should be done, right? You set up an axiomatic system, and you proceed from there. You ask, what can we prove? But it was only seen as a shining example until about the 1850s. Until, let's say, 17th century. Today, it's seen as the total opposite. It's an example of really lacking mathematical rigor. So today, viewed as lacking. Mathematical rigor. But to put this in context, again, yes, there's lots of criticisms of the elements, and they're all warranted, but this stood for 2,000 years, right? People use this for 2,000 years. To put this in context, this is still really good, really amazing work. All right, so why? What's wrong with it? Well, there's quite a lot. I'll list a few things here. Part A is, remember, he only has these 5 postulates or axioms, right? By the way, those words usually today, to Euclid, postulates and axioms were slightly different. Today, no one sort of recognizes it as a distinction. But one is he's constantly, in just about every proof, he basically comes up with his new axiom without stating it. He's got lots of things that he assumes to be true without actually axiomatizing them. Right? So one is he's constantly, he does this all the time, constantly takes things for granted. This can be very subtle, but constantly takes things for granted that aren't axiomatized. Axiomatized. Some examples is he has two circles that obviously intersect, and he says, yeah, these circles intersect here and here, but if you want that to be true, then you need to axiomatize it. There's very subtle things happening, but B, by the way, all of these criticisms, again, this is sort of geometry 2 stuff that we'll get into. Definitions. Let's say he tries to define everything. This wasn't recognized as a problem until very recently, past 100, 200 years, which is, you might think in mathematics everything needs a definition. That's reasonable, that's the approach Euclid took, but it turns out that doesn't work. So, something like a point. He tries to come up with a definition of a point. And I believe he says, a point is that which has no part, or something like that. Right? This is a definition of a point. Well, then the question is, what's a part? Then you have to define what part means. And then in your definition of a part, you have, okay, I have to define what this new word means. So in modern day mathematical theory, people recognize that some things just, you don't define them, right? Everyone understands what a point is. We don't have to define it. It's sort of like these 5 axioms. We'll accept this as true. We accept a few basic terms that don't have definitions, that we all just understand. So this is a big problem for Euclid. And C, this is most relevant to us in this class, is he does a lot of proof by diagram. What I mean by that is he relies on pictures way too much. And a picture is not a rigorous proof, right? A picture can lead your intuition, but it's really just a proof for that particular picture that you've drawn, right? It doesn't extend in full generality to all possible triangles or anything like that. So, lots of proof by diagram. And that's the big problem. That's no longer considered a rigorous proof. But that said, I mean, I'll give you an example. Things like, okay, here's a triangle. Here's a triangle A, B, C. Let's bisect this angle A. So I'll draw the line bisecting it. Where does it intersect this side length BC? Well, let's say it intersects right there at Q. Is it possible that the bisector of angle A doesn't intersect this side of the triangle? No, right? It always does, and by a picture, it's pretty damn obvious. But still, it's not a proof. It's not a rigorous proof. So these need to be done, right? Something like this, this very simple statement, it's very obvious from a picture. No matter how you draw this triangle, right? You can draw triangles all day, it's very obvious. Even simple statements like this, they require rigorous proofs. And Euclid just doesn't do that. The problem with rigorous proofs like that is it's very dry, right? And it's not exciting. It's not exciting to prove things that are already obviously true. It needs to be done, but we won't do stuff like that in this class, right? Because one, it's not exciting. Two, it's kind of frustrating to prove things that are obviously true. And three, yeah, if we spend all day on this, we just won't ever get to the very exciting results. So we will be a little bit lax in this class. Sometimes I will prove things by diagram, but again, it's not totally rigorous. So proving these simple statements, can be kind of dry. Can be dry, but must be done by someone else. So who did this? Like I said, all these criticisms came about. People started to work on this, and I believe it was 1899. Hilbert comes in. 1899. We get Hilbert's geometry. Which did sort of Euclidean geometry. He was the first person, I believe, to do it properly. So instead of 5 simple postulates, 5 simple axioms, he had 20 axioms, which unfortunately you need some of these things. So this is 20 axioms. And this has been redone by other people since. We've got guys like Birkhoff, we've got Tarski. There's some other group, I forget the group name, that will actually use their axioms in geometry too. But this has all been done properly since, and the point is, if you want to do this very rigorously by today's standards, you need a lot more things that Euclid just didn't axiomatize. Any questions? All right, so we'll be going through Euclidean geometry in this class. Again, we're not going to worry about all of this stuff, what Euclid did wrong, what he didn't. We're not going to study his postulates in detail or anything like that. Again, most of this history, all of that stuff is geometry too, which I think is super interesting. But in this class, we'll just be going through some of the results of Euclid, some further results that aren't in the elements, results by Cheva and Menelaus and stuff like that. So yeah, we'll get there eventually. I'm not sure how long it's going to take us to get through everything I've listed. I want to go through the first 2 chapters for sure. Chapter 1 is just recalling some of the basics. Chapter 2 is more stuff on triangles. Then we'll do some of chapters 3 and 4. And chapter 6 is really ancient stuff, these interesting questions of what can you construct just using a compass and a straight edge. At that point, I might ask you to start bringing a compass to class so we can construct some things. But that's no time soon. And yeah, we'll see how long that takes us. The really nice thing about teaching a class like this is, in calculus or something, you have this very strict schedule that you have to stick to. Here we can do whatever we want. So we'll probably have some days where we just slow down completely, just work on proofs in class. But we'll see. No questions? Hey, what time is it? It's time to go. I'll see you guys on Wednesday. Oh, by the way, I haven't decided on my office hours yet at all. I think I might just do them immediately after this class every day. We'll see.